Welcome to combustion analysis, and that will be our focus for this lecture. Okay, combustion analysis. We're going to combust something, in this case a hydrocarbon. So in here we have this chamber. Okay, we'll call it the furnace because we're going to apply heat to it. And that's our substance. Organic meaning it contains carbon and hydrogen, really carbon. But we'll have carbon, hydrogen, and likely oxygen involved in this. But it doesn't have to. But carbon and hydrogen, that's what you're going to have in there. So you put this in here, and you're going to put a lot of heat on it. Well, the fire triangle is made up of your fuel, oxygen, and then a source of heat. So we have heat, we have our source, we have to pump oxygen through here. Okay? So we put it in there, and then it gets hot enough, it goes, okay? Well, we're forcing oxygen through, so everything is traveling this way. Well, what do we have here? We have a water absorber. What's always a product of combustion? Well, two things, carbon dioxide and water. So the first thing this hits is a water absorber. So all the water that was made from combusting this will be contained in here. Well, if you note this, in combustion, it always turns into water and carbon dioxide. Between those two, this is the only place for the hydrogen to go. So all of your hydrogen will theoretically be absorbed right here. Okay? And so this carbon, hydrogen, oxygen containing material, all your hydrogen is going to go right in here. Over here you have a carbon dioxide absorber. Theoretically, all of your carbon will be absorbed in here. Okay? What about your oxygen? It gets a little complicated here because they both contain oxygen. Oxygen will be split between these two, and oh, by the way, we pumped in oxygen. So you have two sources of oxygen. What was here, and then they're both split up between here and here. But we'll account for that later, and we'll figure out what the accurate amount of oxygen is. All we know is when we combust this, we theoretically absorb all the hydrogen in the water absorber and then all the carbon in here. And what we can do is we can weigh this before and after. Whatever weight this goes up by, well, that difference was made by your sample and how much turned in here. And we're going to analyze all this to then find this empirical formula. Okay? So this is functionally what happens in the laboratory. Okay, so we originally, that green, well, yours is gray, but right there, green right there, we said that's a 2.04 gram sample. Okay? Of what? I don't know. That's why we're doing this. But we do know we can do different tests to figure out what elements are present. We do know it has carbon, hydrogen, and oxygen. And when we combusted it and we pumped oxygen through there, we ended up, our carbon dioxide absorber, it gained 4.49 grams, okay, of mass. And our water absorber, it increased by 2.45, okay? So now, based on this information, how much did you start with, how much was captured, we need to find the empirical formula. Okay, this is what you're thinking, okay? Read over that. What we're ultimately going to have to do here is we're going to find the empirical formula, obtain using the masses we obtained in step one. Okay, and we don't have to make the assumption that we have 100 gram sample because we're not dealing with percentages, right? We're just going with what we actually were given. Okay, so you got a chance to look over that. Now let's start applying this one. Find the grams of carbon. Well, carbon, but we're starting in carbon dioxide. Okay, stick with me. We had this much in our carbon dioxide absorber. Well, let's get into moles then. You have 4.49. Well, for every 1 mole, you have 4.40. You divide that, you're now in moles of carbon dioxide. Well, now that you're in moles of carbon dioxide, what's your ratio? If you look at the formula for carbon dioxide, for every 1 carbon dioxide, how many carbons are there? There's 1 carbon for every 1 carbon dioxide, hence the 1-to-1 ratio. Okay, now that we can see that, we're back in a 1-to-1 ratio. Well, now we wanted to know, find the grams of carbon. So for every 1 mole of carbon, there are 12 grams of carbon. Okay, I normally call it 12.01, but we cut it off here. So now you just do your math. Let's cancel all our units out. We're left in grams of carbon, which is where we want to be. Time to do our calculations. You get 1.22 grams of carbon. We come over here. find the grams of hydrogen. Similar process. Well, we're dealing with water from a water absorber. Well, let's take a look. For every one water molecule we want to have a hydrogen, there are 2 hydrogens. So that's why we need to get from grams of water to moles of water. So we got 2.45 grams for every 18 grams of water, there's 1 mole. Now we use this 2-to-1 ratio. Okay, for every 1 mole of water, there are 2 moles of hydrogen. That's your 2-to-1 ratio there. Now let's jump back and get into hydrogens. For every 1 mole of hydrogen, there's 1 gram of hydrogen. Okay. Sometimes you might want to use hydrogen as a diatomic molecule. This is not in gaseous form. Okay, so when it's by itself floating around, yes, it's H2. Otherwise, you just treat it as a single molecule, and it's accurate to put 1 gram there. Okay, so now we have 1.22 grams of carbon and 0.27. Remember, we had heat. Okay, that's external to this whole process. We had our fuel, the organic sample, and we had oxygen we pumped in. So that means the only way that 1.22 grams of carbon could have got into that carbon dioxide absorber was it came from the fuel. It came from that sample, that organic sample. Same thing, 0.27 grams of hydrogen, but hydrogen came only from the sample. So because we have these two, we need to figure out how many grams of oxygen we had. Do you remember what the total sample was? It was 2.04. So if we take our total mass of all the carbon, hydrogen, and oxygen in that sample, we put it in there, 2.04, and we subtract the amount of carbon and hydrogen that we calculated, you can figure out the remainder is the oxygen. 2.04 minus the carbon minus the amount of hydrogen, and you wind up with 0.55 grams of oxygen. Okay? Now we have grams of all three. We have grams of carbon, grams of hydrogen, grams of oxygen. It's time to now divide the grams and go into moles so we can calculate the empirical formula. Okay, we took our grams, finding their actual mass on the periodic table, their molar mass on the periodic table, and we go here, here, and here. And you can see these numbers, that's the amount of moles. Which one's smallest? This one or this one? This one is. This one or this one? This one is. Divide them all by 0.034. And let's see what we get. That'll be our next slide. Divide them all by the smallest value. And we did that. We get 3 carbons. We get 8 hydrogens. We get 1 oxygen. So they have their C, their H, and their O. 3, 8, 1. That is combustion analysis. Okay? It's pretty heady. It might take a few times to work your way through it. Try some of the example problems. Best of luck.